Everybody, it is Thursday. It is 9 a.m. Pacific, and you know what that means. It's time for OpenCV Live. We are just getting started on this unseasonable warm Thursday. I am here in the fragrant Soma, downtown San Francisco, California. And our guest this week is Alex Hatch, CPO at Backyard Brains. Alex, where are you joining us from?
I am just outside of Detroit in Hazel Park, Michigan.
Right on. Love to have a fellow Michigander on the show. I grew up down here,
Okay, yeah.
opposite side of the state.
Yeah, my dad
Um,
lives over there actually, so.
okay, right on. Glad to hear it. So yeah, folks, wherever you're watching out there, wherever you're joining us from, we're live on Twitch, LinkedIn, live video, YouTube, Zoom. Let us know where you're joining from. We'd love to see it, and I'll also I can bring you up on screen if you do so. It looks like we're good everywhere. So we got people chiming in over on Zoom already. We love to see it. Thank you, Zoomers. Carlos Nava says hugs from Baja. We love to see the homies from Baja, California. This is going to be an all Michigan episode of OpenCV Live. Dr. Satya Malik is on assignment, which means that he's traveling today, and so he won't be joining us, but it's okay. We've done it before. We'll do it again. So long as we have each other, we'll get through this chat. I see hi from Florence, Italy over in Zoom as well. Love to see it. OpenCV is a global community, and it's awesome to see the global community saying hey. Alex, you got some stability issues here today.
We're getting some spotty. Luckily, it connects right away, so apologize about that.
It's all good. We'll figure it out. We've got Twitch saying hi. Good morning to Twitch. Thanks for confirming that you're alive. We appreciate it. It's been a long month or so for OpenCV here. We've been traveling a bunch and meeting new people and hanging out with old people, but it's good to get back into the swing of things with some regular OpenCV Live content. We've got Stefan from Vancouver, Canada. Looks like got Tech Miller from Atlanta, GA in there. How far away do you live from Bad Street? I got to ask. Just one for the pro wrestling fans out there. We've got Timothy saying hey over on YouTube. Love to see it. AI Engineer Spain says he's getting no sound on YouTube. If anyone watching on YouTube can confirm. Looks like we're good everywhere else, so I'm just going to assume it's a you problem, dude. But we'll fix it if there's a problem. Yeah, I think... okay, they're saying Phil's mic is really low. Let me go ahead and adjust my mic here. How's that? Is that better, guys? Am I coming in? Hello, Dimitri. We can hear you just fine. Am I fine? There's a Dr. Strangelove for you guys. That should be a little bit better. Sorry about that. We had some issues last week with my mic cutting out, so the solution, for if anyone was actually interested in that, the solution was a new USB cable. It was bound to happen, right? They don't last forever. But it's very annoying when you need one that's just not the right. You don't have the right length in stock. I mean, everybody obviously has a giant box of various cables of various lengths that they carry around from apartment to apartment and house to house, like some sort of nomad. But in this case, I had to actually go physically purchase a USB-C cable of the correct length and speed, which was a humbling experience, let's say. When was the last time you had to buy a cable, Alex?
I don't know. I have this addiction to the color blue, and so when I find a good one, you just jump on it. So relatively often, I'm keeping up to date, making sure all my stuff is good. So I stay on top of it.
that's yeah. You got to stay on top of your cables,
Yeah.
That's how Fender gets me with guitar cables, is they'll bring out the baby blue ones, and I'm like,
oh yeah, 100%. It's very dangerous.
So supposedly they're also releasing an officially licensed Godzilla distortion pedal I read about the other day, which is again like just take what little money I have, you bastards. You
Yeah,
got me. You got me.
music stuff is a whole other category, and yeah, it's easy to
Okay.
lose your whole wallet, man.
It sure is. Okay, I think now is a great time to get started. Let me go ahead and solo myself here, and I'll do the thing. Hey there, everybody. Welcome to OpenCV Live, episode 209, I think. I am your co-host with the co-most, the second banana who's second to none. I'm also your plus one and only. It's Mr. Nelson if you're nasty, but you, my dear friends, can call me Phil. And I'm here to remind you of a couple of things we do on every single episode of this show. But first, I'm just going to say quickly, hey, to our guest, Alex Hatch. Alex, you want to say hi to the good people out there before I let them know the skinny on the episode today?
Yeah, hi, I'm Alex.
Glad to have you here. So, if you folks need a reminder you're joining us for the first time, we do a couple of things every single episode. The first of which is a giveaway to you out there in the audience. Later on in today's episode, I will be asking a trivia question based on today's episode, so pay attention out there. Then I'll be asking a trivia question. The first person who answers it correctly in the chat will win the OpenCV University course of their choosing. That means that you can go to opencv.org/university, pick whatever course you want, and you will get it absolutely free. That's coming up in about 40 minutes. Pay attention and be ready to win today. We're also taking questions from you in the audience as I try to bite my microphone. I don't know what happened there. We're also taking questions from you in the audience. Use the chat system wherever you're watching on the wide, woolly world of Albert Gore's internet. We're live on YouTube, LinkedIn, Twitch, and Zoom here today. So ask those questions. I will bring them up on screen later on. We can kibitz a little bit with our guest, Alex. Pretty much anything's open here. I think, obviously, no trade secrets. Probably that's about all that's off limits today. So get those questions in anytime. I will then put them up on screen later, and we'll answer some of those questions. But before we get started with the presentation, just a few more bits of business here to take care of. OpenCV is a nonprofit organization that makes open source software. And as such, we depend on the support of individuals and companies, possibly like you watching this. You can help OpenCV by donating via PayPal or Stripe. If you want to use a card, you can do that here on opencv.org/support. We really appreciate it. You can also join OpenCV's Patreon, which we just opened up recently. People who join the Patreon for $7 a month get episode downloads of every single episode of OpenCV Live, DRM free, surveillance free. You can watch them however you want, whenever you want. Put them in your Plex server, put them in your Jellyfin, whatever you got. If you work for a larger company, consider asking your boss about matching donations. OpenCV is part of the Benevolent Causes system, and as such, if you work for a company like John Deere or Microsoft or Meta, you can donate $100 to OpenCV, and your boss can make that a $200 donation without you having to do anything extra except let them know you did it. So please check that out. You can also sponsor OpenCV on GitHub. We have a bunch of awesome sponsors over there. We really appreciate y'all. 15 of them as of right now. I'm going to give them their 5 seconds of fame. We got a funny hi, who's brainstorming right now. We got Alberta Beef, one of the best usernames on GitHub. The homies at RoboFlow, Bears Dev LLC, Axel T81. Sounds like a really cool calculator. DJ Greenwood on the 1 and the 2. Sarnev. Wasn't that Spock's dad's name? Luxtronic AI. Alexander Voronov. Big Vision LLC. iPop AI. Comet ML. Alexander Ismailov. Tala Hussein. And Nick Libertini. Thanks so much for your support, everybody. We really appreciate it, and we couldn't do this OpenCV stuff without you. You can also buy a t-shirt, bag, or other official OpenCV merchandise on the official OpenCV merchandise store, opencv.myspreadshop.com. Every purchase goes directly to the development of OpenCV. You can get t-shirts, hats, stickers, pins, bandanas for your pets or children. Put them anywhere and wear them proudly. And send us a picture of you wearing the stuff you buy. We would love to feature you on the show here on OpenCV Live. Before we get started, again, one teeny tiny thing to take care of. I want to thank our members and partners. OpenCV depends on the support of these folks: ARM, FutureWay Technologies, Google Summer of Code, RoboFlow, Orbic, the British Machine Vision Association, JetBrains, Edge AI and Vision Alliance, OpenMV, Tangram Vision, Amped Software, Intuitivo, Rerun, Intrinsic, Bears Dev, and Big Vision, because every company needs a big vision. Okay, folks. So, Alex, welcome back. Your internet connection is increasingly erratic.
Yeah.
It's going to be a fun episode. Strap in, everybody.
It will be. Yeah, and we've got demos, so always something magic when you've got a demo, right?
Absolutely. All right, Alex, I'm going to go ahead and give the people a quick little intro about yourself before we get started here.
Yeah, I've got it on my second slide here.
Fantastic.
I guess
go ahead and just bring up your slides then.
Yeah, sounds good. Even before I get into myself, I guess what we're talking about today, and let me know when you see me my slides.
I don't have your slides for some reason. Go ahead and bring them up.
Oh, maybe I have to reshare after the connection there.
Yeah, it looks like it. All right, here we are. We get the cool Drosta effect. No, we didn't. We skipped it this time. Okay. Take her away, Alex.
All right. So what we're talking about today is building brains for robots. And we're doing this with a product we call SpikerBot. This is a new invention of ours. We'll get into all the nitty gritty, but it's basically a small, remotely operated robot and paired with an app that you design your own biologically plausible spiking neural networks. So sort of like a different programming language. Thank you. Yeah, it's pretty exciting. It's been a long time coming. So before we get into that, a little bit about me. My name is Alex Hatch, aka the Blue Man. I'm a product designer and roboticist with over a decade of experience. I do everything from 3D design and CAD, electrical engineering stuff, getting into just everything I can get my hands dirty with. Woodworking, circuits, programming, 3D printing, plastics, you name it. I'm trying to get into it. Yeah, it's hard to exist in the modern era and not take advantage of everything we have access to. Open source has always been a big part of my life. OpenCV is an amazing thing. We actually use it in our product here. We'll talk about that a little later.
Radical.
And then everything that we do at Backyard Brains, which is who I work for, is also open source. And so that's how I really have come to learn a lot of things. I'm actually an art school dropout. And so most of what I know is through osmosis of standing on the shoulders of giants online and people I meet, and just building these skill sets slowly over time. So something that I firmly believe.
You couldn't get any cooler. I'm going to outcool you, though. I'm a high school dropout.
Right. Awesome. I think it's excellent. I mean, we live in I think the most accessible time to be a dropout, and it's one of those things. It's a wonder what we have access to. When I was in college and everything, I actually left to go work in an opportunity with Backyard Brains, and I just couldn't look back. It was like once you get a taste for what's really out there, all the exciting things that we have access to, it's like you just go. So yeah, it's I don't necessarily advocate everybody drop out of whatever program they're in, but
don't live like me, people. Don't do it.
It's life will take you strange places. So coming from Backyard Brains is this neuroscience education company. We build all these different devices. When I first started working there, I worked on building microscopes and some early ePhys rigs, things that work with Arduinos. We briefly were going to be working on a microbit, little bits. I don't know if you remember those. We were working on an amplifier for those that we could use our own muscle signals. And so we're working on all sorts of different things. I left for a handful of years, and then in 2022, I sort of got a call back from Backyard Brains, and Greg, his first words were something about like, hey, do you want to work on this robot? And then I kind of tuned out the rest of it because I was already in. So this has been what I've been working on him for the last 4 years, and it's been a blast.
Backyard Brains strikes me as an extremely Midwestern company name.
Yeah, it is. And it has also got that vibe. I mean, even when I wasn't working there for a good number of gap years, doing other things, running my own successful and failure businesses, and working at Ford Battery Lab, doing trade show exhibits, getting my first patent recently, all that stuff. We always maintain contact. Yeah, thank you. There's a big achievement. I've tried it a few times, but we finally actually went all the way through on an invention recently. So that was pretty cool.
Awesome.
Yeah, thank you. And so, yeah, Backyard Brains, though, always been going to their holiday parties and everything else. So beyond just the name, it's very much a Midwest vibe of a company, I guess.
Are they brewing beer in the backyard? That's what I have to know.
Not currently necessarily, but
yet.
we're open to it. Yeah, I mean, we gotta find a neuroscience hook that we can teach people. So we'll see.
I mean,
coming soon.
Get the robot brains drunk, obviously.
Yeah. Well, we don't deal with neurotransmitters quite yet, but that'll come up, and yeah, maybe that'll be something we play with. There again. Whoop.
We lost you, but you're back.
It seems to be blipping on. I hear a little noise, so hopefully we won't miss too much.
It'll be fine. We'll make it work. Well, quick comment from the Peanut Gallery. Our friend Martha Gorham, who has watched like every episode of the show, says, I admire Alex's speech because I had to abandon my interest in electronics in 1962, and now I'm learning KiCad. Love to hear it. It's never too late to learn new stuff. Like, I feel like people are very doomy about that, oh, you get older and it gets harder to do stuff. And yeah, it totally does. But that doesn't mean it's impossible. Like, you can still do it,
Yeah, and I'd argue it's probably easier than ever to actually learn new stuff. And I'm a huge proponent of like late learning and just going through that journey. I mean, I think it's something that we tell ourselves. Yeah, it is difficult. It's harder to learn a language. Your brain's not as plastic when you're older, but we have more resources than ever. It's at your fingertips, and it just takes your willpower to kind of persevere and get engaged with the things you want to do. Especially there's a lot of people too who go through their whole lives working for the man, so to speak, and then they get to retirement and they don't know what to do with themselves. And that's the perfect time to start learning some stuff, pick up some new hobbies. So yeah, awesome. So a little bit about Backyard Brains. If you're not familiar, we are an open source neuroscience company. And so our goal is to kind of bring neuroscience education and understanding to the masses, inspire young minds to get into the field. Greg Gage and Tim Marzullo are the co-founders, and they started this company as PhDs when they were during their PhD program, and they wanted to basically make affordable gear to replicate what these like $40,000 rack machines that they were using to study were doing. And so we've done tons of stuff from a lot of electrophysiology stuff, starting with insect electrophysiology, amplifying signals in cockroach legs and dragonflies and grasshoppers. And then we get into stimulating insects as well. And then to human electrophysiology, into even more recently, plant electrophysiology, which is not directly neuroscience, but it's all related. We all have electrical signals to send messages. And so it's kind of an important thing to kind of see all of these parallels between different forms of life.
It sort of sounds like a non-evil version of the organization from Kamen Rider, with all of the grasshoppers and spiders and stuff like that. Shout out to my tokusatsu fans out there.
Yeah, I'm not as familiar, but I'll have to check it out. Yeah, I mean, and one of the big things that came up, so Greg was doing a lot of TED Talks and stuff, especially early on in Backyard Brains history. And one thing that when I started a few years after Backyard Brains did, that always stuck with me was this idea that, roughly at the time it was 1 in 5. I think that ratio has gotten greater, but 1 in 5 people suffer from some sort of neurological disorder, be it something simple like ADHD, into autism, even things like schizophrenia, all sorts of different afflictions. And we don't have any cures for any of these. We have treatments, we have medications, we have therapy, but I think that a lot of what society faces is, sourced in the brain. They're human problems made by, what's up here, right? So getting a better understanding of, the brain, getting people engaged in the field, I think is just a net positive thing for us to invest resources in. And so, the thing is we've been dealing with all these electrophysiology gear, and we do a lot of hands-on demos. We show sort of these cause and effect things, dealing with neuroscience, measuring, the sort of quantitative things about neuroscience, how fast a neuron sends its signal, different effects of like pharmacology and all sorts of different things centralized around ephys. But if we want to actually answer that first, problem of, well, how does the brain, come up with all these disorders? It's beyond just the chemistry. It also has to do with how the brain is wired and how it sends its signal. And so something that I think we sorely lack in the education space and, society as a whole is an understanding of how a brain actually computes and thinks about things. We find it's very different than, a classical computer. And we'll kind of talk about that a little bit later. But this is an important thing, and this is something that SpikerBot sort of aims to start guiding you into this understanding and process.
Super exciting.
And so a little bit about SpikerBot and how it came to be. I have to talk about my colleague, Christopher Harris. He's a doctor of neuroscience, and he's been working on this for probably over a decade now. He came to Backyard Brains during my gap years, actually, and around 2017 co-wrote a grant with Backyard Brains and started this whole journey of bringing neuro-robotics to the classroom. So, neuro-robotics being robots that you are basically using simulated spiking neural networks that are real-time, that are biologically plausible versus using classic lines of code, everything that we're probably familiar with OpenCV and a lot of the speakers. This is a whole different way to think about things with its own set of challenges. And so over the years, we've secured up to, I believe it's $2.8 million in funding from NIH and NSF. And we've used this to do everything from actually developing things. So Chris built the first prototypes, which were these larger robots, along with some of our engineers on the team. And these larger robots would communicate in a similar style where you have a peripheral. It sends its data over to an app. In this case, it started as a MATLAB app. And you run our simulation of neurons that you design. And then you stream those actions from those neurons back to the robot for it to perform. And so this all happens in a sort of a closed back and forth loop. And we basically took this, and Chris did tons of workshops. We work with educators across the country and internationally. We built high school level curriculums that teach really important neuroscience concepts, especially in the neurocomputation space. And we did tons and tons and tons of refinement over the last decade, basically, to get this concept refined to this phase. So when I came into the project, this was towards the end of our grant series. And so I was able to do some of the education, absorb sort of like the last of the lessons learned. And then I took that stuff and we sort of started running with turning this into the actual product, which we are finally launching. So,
and those NSF grants are not easy to get. We know from experience here at OpenCV. We applied for a few a couple of years ago, and it's a thorough vetting process, and you really have to lock in your messaging and everything on these docs. It's tough.
Yeah, there's a lot of grants that we apply for too, and we don't end up getting. The thing is it's also been harder in more recent years.
Yeah.
But they're very important, and for us in the space of neuroscience education, it's a field that gets lost in the soup of STEM education. You know, you have science, technology, engineering, mathematics. At one point, it was STEAM. They had art in there, which I think is great.
Yeah.
But neuroscience isn't in the acronym, even though it really touches base with every discipline within that. And again, you know, my feelings are that it's some of our largest societal problems that we should pay more attention to. So,
Agreed.
it's been an interesting journey though, and I think Chris's work really is what enabled all of this. You know, his ideas trying to bring what we see and some of these other things to life is very important. So, going on from that into just a brief history of neurorobotics, and I believe I have a book here next to me, but neurorobotics is something that has existed probably since, you know, as early as the 50s. And the idea is, you know, instead of using sort of classical computing, at the time there really wasn't a lot of that. The idea is that you're using really simple sensors and you're using their actuations to drive motors to produce behaviors. But by linking these sensory systems almost directly into the outputs, you get these really complex emergent behaviors. And this is also what we see in biology. So this is the book that's an instant classic. It's Breitenberg's Vehicles. So Eugene Breitenberg basically created this. And the idea here is, sorry, not Eugene. I'm thinking of a guy later, Eugene Isaacevich. This is the Valentino Breitenberg. And so, but the idea behind this, though, is this is an exploration of these simple vehicles that you can construct using like little light sensors. And so on the right here, I've got an image of sort of a left eye controlling the right motor and a right eye controlling the left motor. So you get this crisscross action. And so whenever one of these eyes sees light, for example, it'll drive one of these motors forward. And so two really classical examples, he explains, if you have parallel connections, where the left is connected to the left, right is connected to the right, you'll get a robot that will want to avoid looking at that light. It'll want to turn away because it'll instantly kind of push. If something's over here, I'm going to push my body sort of away from it. If you crisscross them, you'll get the opposite behavior. And so this wiring and sort of how we connect the sensory systems is really key to the complexity of behaviors. And this is what we find in biology. And it happens pretty quickly, getting some unexpected things to happen. So it's pretty cool. You know, compared to like driving a regular classical robot, you can do some things with a very minimal amount of effort.
It's like robot fear factor over here.
Yeah. And so, you know, here's an example of what that looks like. So on the left, we have our app. This is replicating that same Breitenberg vehicle that is emulating, you know, a love behavior or attraction or a, you know, sort of predatory behavior of tracking down an object. And then on the right is sort of a, you know, pseudocode snippet of what you might expect to build a robot in C++ using like OpenCV libraries. And so on the left, we have these extra connections that I light up some lights. We'll go over the interface more hands-on a little bit later, but I take the camera feed. This is sort of an anthropomorphized top-down of our robot, which I'll show you here. It's this little guy. So we're looking at it from the top down. And so you've got the camera.
Let's see that robot a little bit more.
Oh, sure. Yeah. So our logo is the brain in the wheelbarrow. Cool. You can see on my chest. And so this is sort of that personified also as a little robot. He's a little AA battery-powered guy.
Oh, okay.
And he's got all these different attachment points and little face that you can customize and do some more things with. So we'll definitely be getting some more hands-on after kind of breezing through the rest of this. But
is there a cute nickname for the robot?
You can rename it however you like. It's always going to be called SpikerBot something. This guy is SpikerBot Aqua, and he's got a little blue heart emoji. But you can put him whatever you want. Yeah, everything's got to be blue, so naturally. So yeah, in terms of this interface, so we got the camera, we're tracking the color blue. We have 2 neurons, and then you can see this crisscrossing controlling on the right. These are our 2 motors. So we're controlling the forward motion of the motors, and we're showing different lights to just sort of indicate what the robot's seeing, give it a little bit more visual interest. And in the code, we're kind of doing a similar thing, capturing the camera. We are looking for specific colors. I think in this case, we're looking actually for red instead of blue. And so we filter out anything that's not red. We would have to, do this math to mask things out, find a blob. On that blob, we would want to actually control the motors and maybe have a little PID loop. But this is not something that you're going to do in 5 minutes the first time, experiencing code.
Oh, looks like we lost our Alex once again. I'll bring myself back on here as we wait for our guest to return. I will chit chat with the audience here a little bit. As a reminder, folks, we're taking questions from you in the audience, so drop those questions in the chat wherever you're watching, or put them in the Zoom Q&A button.
But detecting faces.
That'll help me deal with it. Hey, Alex, you're back. All right.
Sorry about that. I'm not sure when I dropped out.
A little bit, yeah.
Was I talking about the code still here, or?
Just a little bit. I think you had just said this is not the first thing you would do.
Yeah, so this is basically just not the first thing that you would do in about 5 minutes of, hey, I want to program something. Like, it's going to take some foundational stuff to get to the point where you can create this code. Whereas if you are to program our robot and use neurons, you can do this in 5 minutes. And in fact, we had preschoolers, tinker with these brains, make modifications, and adjust these things real time and have a blast. So something that's useful for kids to start just playing, but it really can take you all the way through like later education. And the important distinction here is that our brains and neurons are very much unlike computers as we know them. We are used to, the things that are easy for a person are usually very hard for a computer. And you can kind of see that illustrated here. 2 neurons versus, a dozen or so lines of code, not including libraries and other specificities. But also that is also true in the inverse. And so something that is easy for a computer, like counting in binary, you can just, have a variable every loop, you can give it a plus plus. Counting is something that is doesn't come naturally. And we have to learn that process to actually really build up a lot of concepts and make associations in our brain before we can start getting into math. So it takes us years of our lives to get to the point where we can actually start doing these things. And so this is just kind of the interesting thing that we'll see, especially when we get into the demos here. So just a little bit of a background just to get through the technical stuff. We are building off of the Eugene Izakevich Integrate and Fire model. And so this was a model developed in 2003. And it's a mathematical model that was basically developed, obviously, for 2003 hardware. So we're not blazing fast here with tensor GPUs or anything. But in 2003, you can basically simulate hundreds of thousands of neurons with various spiking behaviors. Using our main 2 classes of neurons, our excitatory neurons, which make other neurons want to fire, and our inhibitory neurons, which make other neurons want to quiet down when they fire. And so this is a little snapshot from our interface. You can access that model directly, although we really like to abstract things to make them simpler so that people can get started a lot quicker. And so it's awesome, especially during all of the back and forth with educators and sort of condensed a list of possible spiking behaviors from a lot of these papers and from a lot of the functionality of building these circuits into an awesome list that we can use. We'll describe later. But if you're interested in the math, this is basically the whole differential equations and rules for actually running these models. Basically, all your neurons and connections are all in parallel. They have a sort of resting membrane voltage, just like a real neuron. And when you make a connection from one to another with an axon and a synapse, we can send the current from one when it spikes to the next. The weight of that synapse will sort of change some of these variables, but we essentially are just integrating this voltage over time. When we reach over a certain threshold, the signal will rapidly spike and then collapse back down below a resting state, and then it will have a refractory period where we basically have it relax back to its resting membrane potential. It's ready for a new signal. This is just how our regular neurons work because of the chemical component to them. And you can adjust these parameters just in tons of ways to get a lot of behaviors that you'll see in like this model specifically was really building off of the cortical cells in mammals. And so this is like the outer layer of your brain that does a lot of heavy computation. You see a huge variety of spiking patterns.
Oh no.
Did we lose me there again?
Yeah,
okay,
all
cool.
good.
Cool. Hopefully that one was quicker and we didn't lose too much there, but
No, you're good.
So briefly, so that's the model that's running under the hood. That's sort of the most important thing. And then we are at an OpenCV live. So we'll talk a little bit about the OpenCV, which is kind of some of the magic stuff. SpikerBot is a camera on wheels, right? It's got some other sensors like microphones, distance sensors, but a lot of really cool stuff happens in early biology and with our robot with its vision system. So, there's a lot of things you can do now with machine learned models and with OpenCV. And so there's two big important things that OpenCV provides for SpikerBot. The first is that it helps us with detection. And so part of the way that we actually interact with the sensors on SpikerBot is to sort of abstract these things down into easily digestible, intuitive interaction. And so you're looking at the interface here. We have a list of our targets that you can select from. We use YOLO V8 for our various detectors. And we also use OpenCV for detecting things like color. And we use OpenCV also in the background for actually doing a lot of the image pre-processing. We need to do all this stuff real time so that we can actually have a dynamic robot. But on the right here is sort of the abstracted interface you get. So instead of writing a bunch of code, obviously we have to have code under the hood. We are working on a real computer here, not with neuromorphic hardware. But under the hood, we have all these OpenCV things so that when you make a connection from the camera to a neuron, each connection has its own instance of an interface of how that neuron will respond. And so you can see we've got a little message here. It says the neuron will spike, which is that signal it sends, whenever SpikerBot sees the color blue in this specific area of its field of view. We have some quick access buttons for like the left half and the right half, or if we just want to see a target anywhere. But then you can also adjust these two different dials or input texts to find an exact little sliver of its field of view that it can respond to. So whenever a blue object crosses that, we'll send a signal current to a neuron that will integrate with all the other neurons in parallel, and we'll get some actions.
Very cool. I love the UI on all this stuff. Is very fun.
Thank you. This is what a lot of the refinement has been. It's been a challenge, going from where we started with MATLAB and simple circles and lines and just sort of like the classic menus and drop downs to something that became visual in the last 6 months to a year. Finally got to the point of polish. So, oops, wrong one here. On a little more technical side in the background, the other thing that's kind of cool is that when we actually are running our simulation, which we'll show in a demo here, we have like a live visualizer that we can see what SpikerBot sees. So it was kind of an important thing for us to not give, especially in the education setting, like just give a raw camera feed. A creature, yeah, I mean, we see with our eyes, we see a whole color field of view. I'm looking at my screen, it looks just like this. But for a robot with a simpler set of senses, we wanted to abstract that quite a bit. And so we came up with our own filtering system and also a way to, highlight and visualize what it's tracking at any given moment in time. A lot of what Backyard Brain style does is these hand-drawn illustrations that you'll see, throughout, like our drawing of our brain here, our logo, a lot of our other illustrations as well. And so we do some cool stuff. We use the extended difference of Gaussian techniques to basically get like a black and white silhouetted outline of our image. So we take the raw image, create a black and white silhouetted outline. I did a lot of stuff with the Game Boy camera, which is a whole different topic. But I learned a lot about like dithering algorithms and all that sort of stuff. And in our style, we sort of replicate like 1920s like printing press shading, where you have a lot of these, elegant, or even if you look closely on a dollar bill, the way they shade, where you got these parallel lines that change their thickness. We wanted to basically incorporate that. So we basically create this sinusoidal half-toning, line work pattern across the field of vision. And then what we do is we take the luminosity. So we already have the black and white. When we take the luminosity, we sort of score what is not part of the outline. We give it a shading value. And then at that location, we'll look at our, infinitely thin lines, and we'll change the thickness of the line at that point. And so what you end up getting is you get these smooth, sort of more illustrated gradients. And we'll look at it in a second here. But it's cool because OpenCV allows us to do this, Snapchat style filter real time on a lot of different hardware. And this also runs on web and mobile devices and all sorts of stuff. So here's like a little small version. We don't have a huge high resolution that we pipe over, but we take a raw image. This is of my whiteboard and a bottle here that we might want to detect. We first do our step to do the difference of Gaussians technique to get sort of just these simple black and white outlines. We apply that sinusoidal dithering algorithm, so you can kind of see that we've got some sort of cross-hatching in these different flowing lines here. And then finally, we'll use OpenCV with our object detection, either color or objects. We'll provide a silhouette, and then we'll like multiply the a color over that and a little marker in the live view, so you know what it's seeing and where. So that's sort of
very cool.
Another cool technique. It's just kind of fun.
Yeah, well, also, I remember we talked, I think when we first met, we discussed the Game Boy camera, maybe at Open Sauce, perhaps?
Yeah. So about a little over a year ago, yeah.
Yeah,
and
we definitely need to have you back on to talk about, he dropped again. But we definitely need to have you back on to talk about your Game Boy camera projects, because it's so awesome. I'm a huge old hardware nerd, and like the stuff you made with the Game Boy camera is like mind blowing to me.
Yeah, there's a lot of really cool stuff, and I'd be more than happy to share. A lot of that stuff is also open source, so a lot of cool things there. And honestly, a lot of SpikerBot's vision was, and my interest in computer vision in general actually stemmed from that Game Boy camera stuff. You can see I've got like a arcade machine here too that I made recently. I think after open source, that's running like an FPGA, analog pockets inside there, and then I actually made a jumbo Game Boy camera, and it's a whole thing. So we got plenty of cool stuff. We can make that a whole episode for sure.
Absolutely.
And then just before we get into our demos here, just a little bit more about the architecture of SpikerBot. So we've kind of glossed over it a little bit, but there's two important distinctions. So the robot is a peripheral. So this has sort of static code that's on here. We have an ESP32. We have our slew of sensors. We were battery powered, our motors, our lights, sound engine. All that stuff is relatively static on the robot. And so what's nice about that is that all the magic happens in the app. And so the app basically will exchange telemetry over a WebSocket from the robot back and forth. We share our camera feed. And then the app can also take in like HID inputs with special neuron types to make like, various triggers. And we do this full loop at about a 20 hertz rate. And so it's just latent enough where you can have pretty dynamic behaviors. But with all the things that we're streaming back and forth, that's basically, it's about like motion picture speed of life. You know, the robot itself then has sensors and actuators, but then we also have some expansion that we're not really ready to talk about yet. But then also these accessory ports, and so you can actually make these 3D printable costumes that are also open source, and you can snap fit all these things into the various holes and features on the fronts and the sides, and so you can sort of customize this guy to sort of match the personality that you give it when you go to program it. The other beautiful thing about the app, and I'm not sure if I'm still online or not.
You are.
Okay, cool. I know it's been spotty, and I apologize. The other cool thing about the app is since the brains and the circuitry and the simulation all runs on the app side, and the peripheral is just sort of on standby, this enables a super rapid pace, iterative development style that allows you to sort of build an intuition faster than really any robotics or programming platform I've used, because you literally you drag and drop, you can alter your connections and what they do, and then you press play, you see it real time, then you pause, and you can just go back and forth, and it becomes an intuition process rather than like the classical critical thinking process that you're doing with traditional code, where you really have to observe for a while and then digest and then reassess, how your circuits work. All these things happen, but the advantage of having this happen at a real-time time scale where I can, fix and tweak in seconds instead of maybe minutes to deploy or, longer, really speeds up this critical thinking process. And so just last little blurb, SpikerBot is actually now live on Kickstarter. So you just search for SpikerBot, you'll find it. I believe that you got some links out as well.
I just put a QR code up on screen. Go ahead and scan that code, folks. Check out SpikerBot. We actually also have a little deal with these folks. If you click our link here or scan our QR code and back them on Kickstarter, we'll maybe get some referrals going that'll help benefit OpenCV.
Yeah, we're tracking all of it. We love you guys. We're obviously using OpenCV in our product. And open source just wants more open source things to happen. So, keep OpenCV alive, keep open source neuroscience alive, and also if you just want to check out some really cool stuff that you've probably never interacted with, now's a great time to do it.
Absolutely. All
right. So before we get into the physical demos, I want to do a little bit of talk about the software here. And so, if you can see, I've got the interface up that we saw earlier with the little cartoon brain. And so I may have glazed over this, but into the Flutter architecture. So MATLAB, the Flutter architecture. And in this architecture, it allows us to do a lot more cross-platform stuff. There's still some embedded systems stuff. There's still native implementations. But right now, when I came in and took over the development of the app, I basically started with iOS and macOS, which is what most of my machines are. And then we got web platform online, which allows us to kind of get to everything. We may do some more native implementations later, depending on some feedback. But we're looking at a Chrome OS build right now. And so if you do want to check this out, you can go to spikerbot.app.backyardbrains.com. We can send a link later. It's not quite ready for prime time. Obviously, you don't have a robot yet, but you can at least check out the interface and sort of noodle around. And so on the top left here, we've got our excitatory neuron. You can drag it into the brain, the senses, the actuators. So I'll drag one onto the camera. You also have an inhibitory neuron, and we could also drag it into the camera. And so we'll drag these guys around. Now, when I click on one of these connections, I've got sort of a default. We're looking at for the color green, but you get information that kind of follows you out through your interface. You can turn that off if you're a power user, but we like to keep it on to kind of tell you what to expect when you start actually running your simulation. So
and
you saw
of course
earlier
you're using the official typeface of science, the XKCD font.
Yeah, it's actually a a custom, we call it Backyard Brains hand drawn. And so we actually had an artist that was doing a lot of our illustrations earlier on. And he was generous enough to let us use some of his handwriting. We generated a font from it manually, added a bunch of glyphs for a bunch of different languages to sort of match our illustrative style. So it is a lot of what you're going to see here is it's all bespoke. So I did a lot of the drawing as well as programming and 3D design of the hardware and some firmware things. So we're a very creative team, very small, but everything you see here is going to be unique. So stop me whenever when there's something that you want to point out. But you can see also I can set a field of vision. So this is sort of this wide screen perspective. The SpikerBot can't jump. It can't, it can move around, right? And so its agency is to rotate, to translate across the plane. And so we don't want to get too complicated too quickly. All it needs to respond to is activity in the horizontal plane, right? And so we have the ability to then set where exactly we want that camera input to be. And so you can see I can make it just a sliver. I can make it a big broad range. And I can click that target, go into a huge list of YOLO targets. When we launch, which will, when people are actually getting these physically, we'll have some more targets and some refined training, such as being able to have a SpikerBot recognize its own species, which will be really awesome for social behaviors, that sort of thing. But you can just select one of these, targets per connection. And so this neuron over here might be responding to the color blue. This one might be responding to the color green, and they can also be looking at different areas of its field of vision. So you can really make a sort of a map of a series of things, or just really high level, look anywhere for a color and do an action. So we make it accessible to get in signals into the neurons. Just a little bit more about the other senses. So I'll drag in a couple more we can look at. You've got your distance sensor. So that's its mouth here is actually a little LiDAR time of flight sensor. And so it can detect things up to like 1.3 meters or 4 freedom unit feet, roughly. And we just do meters. It's a little bit more, I think, user-friendly overall. You can also set in centimeters a specific range. And you can see like a little visualization of what distance an object has to be for that neuron to start firing. So you can make it, if it sees anything, you can make it fire a neuron. If it sees something only far away, you can make this neuron fire. Or only if something gets nice and up close, maybe you want it to fire. And if that's too complicated, we just have a near, medium.
Another little dropout here. Hopefully it will be a short one. This has been a super interesting talk so far. Sorry, we're having some technical issues, but it happens here. That's why we do it live. Anything can happen when it's live. Unfortunately, that means that often anything does happen. So hopefully Alex will be rejoining us here soon. I'm just going to put myself on solo here. Again, reminder, we're taking your questions there. We've got some really good ones in the chat and some fun comments here. Say, such a cute robot. I agree.
Bark Bank.
Very cute robot. Oh, hey, Alex is back.
Oh.
Okay. Welcome.
Sorry about that. I'm not sure how far we lost me. What the last thing I was talking about was.
I think about a minute.
Oh, we lost that long. Oh, sorry. I apologize about that.
It's all good.
So we were probably talking about the camera targets still.
Yeah.
Yeah, I basically just wanted to illustrate. You have the agency to go horizontal here. We can set slivers or large ranges. We can choose our different targets per connection. And so you can really build a field of view of an array of sensors. You can treat it like a compound eye with different cells responding to different things. But what a lot of OpenCV and the YOLO models and everything do for us is sort of do a little bit of pre-processing that you might see in the occipital lobe and turning it into these useful morsels of information. I see a predator in my right field of vision. I need to react to that. I see, a color I like. I want to go towards it. But if you want to get into more complicated things, you can. For the other senses, we have the distance sensor, and so you can use like a near, medium, or far. We've got a time of flight distance sensor in the front. And so this sensor basically allows us to look at things up to 4 feet away or 1.3 meters. And so we can fine tune that, per centimeter to give it a specific range of activation. And Phil, I'll ask you to chime in every once in a while just to make sure I'm not getting lost here. But
yeah, no problem.
okay, cool. Just as a heartbeat here. But yeah, you can set a specific range, and so you can see I'm adjusting the band of activation here. Everything that you adjust will have some sort of visual so that you know what's going on right away. In the microphone, you can look at raw frequencies. So I can set a band of frequencies. In human hearing, we divide these into like bark banks, we call them. And basically one bark bank to the next is a range of signals that we can then distinguish between, this is a lower frequency, this is a different pitch. And so we have about like 24 of these bark banks that are easy for us to distinguish, and then our brain does a bunch of crazy processing, which we could emulate some of that from a really simple standpoint. We don't have hundreds of thousands of neurons in this brain, but you can do really, really small levels of this. Can also just look for volume ranges. So something as simple as a whisper to, somebody speaking or yelling really loud, or, construction noises. And finally, on the microphone side, you can look for specific pitches. So if you're playing a guitar or something, I'm listening for that G, I want to have SpikerBot, give me a thumbs up. We can do that.
Very nice. Very nice.
On the output side, we've got these motors. So each connection to a motor, you'll see I've got a little visual. If I push that right motor forward, you'll see top down, SpikerBot's going to sort of bank left. And if I adjust that synaptic weight here, in this case, it adjusts the speed of that connection. So whenever this fires, we're going to shoot a command to drive this motor at this speed. And the tooltips in here will give you more context as well. So you see it goes fast, and then it's just moving, and then maybe it's going to move slowly. And then if I bring this all the way to 0, it's not going to move when it gets a spike anymore. Every direction will have its own little visualizer. And if we were to send an inhibitory signal to one of these, you'll see that with increasing inhibition, it's going to make this guy stutter more and more. So if I fully inhibit this signal, it's not going to move anymore. Versus if I were to ease off a little bit, every once in a while, let spike get through if there was another signal, and we can do some things.
So cool.
And then just our final outputs here for now. We've got our lights. So there's 4 lights: northwest, northeast, southwest, southeast. You can toggle them on and off. You can set their brightness, and so our whole color wheel here will show you which lights are going to go on. And then you can just pick any kind of color you want. And so when this neuron spikes, you can just have these 2 lights fire. If you had multiple neurons all making different colors, the colors will blend and collide. And this is sort of similar in biology. There's chameleons or color changing squids that have chromatophores. Different cells will be different pigments, and they'll expand in size in the squid or contract when they're not firing. And so this is kind of a similar biological plausibility here. And then lastly, we have sounds. And so it's got a couple different instrument sample types. And we might add more later on that we can play. So you can select one of these instruments, select a note to play with a low or a high octave whenever this fires. But then you also have a bunch of sort of pre-made speech patterns and Furby-esque sound effects. And so it says ciao to say hello, all sorts of things. And then if you're ready for it, the last fun thing before the live demo is just to talk about the neurons themselves, right? And if you're still with me there.
Sure are.
Okay, cool. And so this is what you'll see whenever we select a neuron. Every neuron will have a little editor. You see some things are kind of changing slightly. The little nucleus changed to match the generated nucleus that we have on the one we have selected. And see, these by default are a quiet type. So here's our actual little oscilloscope here. If I test this by, emulating, I can press this button. Whenever I press that, you'll see an event marker I can turn off, but you'll see this spike. So this is the actual, digital currency, the euro of the brain. This is the signal that a neuron will send to another. This is all the messaging happens with these spikes. There's this chemical component, of course. And so this defines a lot of the speed properties of the brain. Unlike a computer, another thing that's very different is that we're not processing at the speed of light because of the chemical component, because of neurotransmitters. Neurons are working on the order of milliseconds, and they travel. There's a measurable conduction velocity, that you can measure in insects even, with a few electrodes you place. And typical neuron is traveling at tens of meters a second. So, a human's, it's not going to take a full second for a signal from your toe to your brain, but it is noticeably more latent than if I touch my face versus I touch my toe. It's why it's easier to stub your toe than it is to stub your face, right?
Stub your face. That's
Yeah, I mean, we have other
an
sensors.
all-new phrase. Yeah.
Yeah, but the idea though is that this signal takes time, and so this simulation runs at about 1,000 hertz, which really isn't that blazing, but it's enough where these little delays matter, and the timing matters for generating events. And so, a single spike is, we're looking at roughly like a millisecond of time here. This is just the most basic neuron, just quiet neuron. We have a huge list. It's not too intimidating. There's sort of 3 classes of neurons. There's ones. It looks like I just dropped out. I'm not sure if you can still hear me.
You're back.
Okay, cool. So the default was quiet. We just selected the burst when activated. This is another neuron that's waiting for an impulse. And you see if I press the spike button here, the test, it's just a little bit thicker. And this gives a more stable connection. It's useful for a lot of our computations. You also have a lot of neurons in the brain that are going to be firing at random. So this one's occasionally active. We use this for sort of pseudo-random events, making sort of clock generators. But notice that it's non-regular intervals. The brain runs on a lot of random noise. And this is kind of one of the interesting things about the brain as a system, is very unpredictable states is very normal and very essential for a healthy brain. We also have these, chattery bursts of activity, very similar to those occasionally activated ones, but you're getting these huge bursts. These are also useful because this might be, if you're prototyping, a good way to simulate sort of random activation of an input sensor. And so you can imagine other input sensors doing all sorts of different things, making comparisons. And so if you want to test things, you can use these other generators, and even ones that are just constantly firing, to actually simulate your circuits. And even with these ones that are generating, if I test my signal here, you'll see I'll still get activations. And so I can still elicit a response, but it will also fire on its own. So still with me so far?
Absolutely.
All right. Last 2, this is where we start to deviate. You can control the Isaacevich model directly. So if you are into the PhD space, you usually can play around with these things. And so I think in this Chrome build, I might have to enter text here instead of use my dials. So it doesn't like to be happy here. But, there we go. We got the activation once we trigger the input. You can see you can adjust these parameters, and depending on how you adjust them, you'll get different activations. So I'm going to do that again to trigger. You see I can kind of turn these things off. Works a little bit better in our other builds, we'll show. The other ones that we have embellished to make this easier, we've got delay neurons. These basically, you set a time constant will release these spikes after some time. And so you can be a really short delay, or you can be a really long delay. So we're waiting for that event to happen. Last one's really fun. This is a remote control neuron. I'm just going to tap some keys on my keyboard here. You can see this guy glows whenever I'm tapping a keyboard key. If I want to respond to a specific key, I could link up an HID device, or I could use my keyboard. I can type F for fire. So you see I got an F now on my neuron, and whenever I press F, it fires. If I press other keys, nothing. So this one's now only responding to the F key. The final sauce is that we link these things by dragging our connections. So I can connect, you always connect from input to outputs. So while it may highlight, I can't actually make a connection in reverse. I'd have to go from source to sink to make new connections. I can also delete them, get rid of them. And then between different neurons, I can set our synaptic weight, which is represented by the line thickness. This is the strength of that signal. So this is saying, the parent neuron will make the next neuron stop spiking, since this is inhibitory, whenever this fires. But this one's excitatory, sending a signal. So it's going to make the next neuron spike usually, or maybe it needs the help from other neurons when it's low, or it'll always make it fire when it's really 100% firing. So these are all the building blocks. I just explained the entire syntax for the whole interaction. Maybe it was a little long-winded, but at the same time, nothing's hidden or no stones unturned. This is the whole programming language. All the behaviors are built off of these simple behaviors of really excitatory and inhibitory neurons. So if you're with me,
yeah, we are.
Okay, let's just kind of give a little bit more of a view. So that says a lot, but what does that actually mean? Well, we also have a whole bunch of example brains. And so we actually sort these by complexity. So we can load up that simple Breitenberg vehicle, but we could also explain this brain. We've got annotations, so you can actually document your work in here. I can pan through and explain what each parts of this circuit are doing, exactly how it's configured. I can edit this and save it as a new file and share it with somebody. So all the brain files that are made in our app can be shared and sent across the world and tested real time, which is really cool. I mentioned earlier, so this is the simple brain, but it makes a complex behavior. Something we take for granted is counting. And so this brain here just counts to 3 in binary, from 0 to 3. So it's counting a 2-bit number whenever we activate the distance sensor. We go through this whole pipeline, and we can explain it by going through this, analyzing all the different functions of this circuit. You can get into the weeds with all this stuff, quite literally with these webs. But this basically is, one line of C code. You have a variable, and every loop you plus it.
This is a really great. I'm really appreciating a lot of the little subtleties of the user interface y'all have put together here, because this is a lot of work. Like, it shows that you've thought really deeply about this, and it's really impressive.
Yeah, thank you. It's like I said, it's really 10 years of going through things, and then when I came in about 4 years ago, I absorbed for the first year or so, and then just kept iterating. I took everything that we'd worked on the robot, the physical side, we threw it away, rebuilt it, took that, threw it away, rebuilt it. I mean, this is this app at this phase, the robot at the phase that we're releasing it at is, we're into the teens of iterations here, not really a 1.0 release. But I just wanted to show you, just before we're about to get into the demos here, but this is something that we take for granted. It's simple for a computer, but look how hard it is for a brain. And this is all these neurons. They all have really specific roles here. We store little working memories. We get a rising edge signal. We do comparisons and almost make logic gates. And we have to, as a creature, build up these circuits. Some, neurons are going to be wired structurally, and you have instincts, of course. But like a lot of what we know about computer science, you don't come into the earth with this background of doing arithmetic, right? We teach each other how to do these things. And so these are some biologically plausible versions of what that might look like. I'm sure the brain does it even more efficiently with more types of neurons. But a lot of these circuits you'll actually find in real biology, especially the microcircuits. So
that makes sense. Yeah.
Are we ready? Are we sick of the nitty gritty?
Oh, we're ready.
Okay, cool.
I'll full screen you here. We can check this out. All right.
So I've got a couple screens here. I'm going to flip us around now, and so got the B cam here. I've got my iMac up there, converted to be a monitor. Blue? So it is. And so
it's stupid that I know the official names of all the colors of the iMacs. I hate myself.
It's a huge inspiration, though, man. I mean, it's the stuff's awesome, and in this case, it's been cool. I converted it to a monitor, so I've got my trash can Mac to the right side over there that's actually serving this version of the app. So just to show that you can run it on a. You might have lost me for a second.
You dropped, but you're back. Yeah, it's all good.
We're quick this time. That's good.
For some reason, your camera's flipped, though. So the text is backwards, but I don't think it's a huge problem.
Okay.
I'm not sure why it's doing that.
We're backwards brains, I guess.
Yeah. Oh, wait, here. I got it. I can fix it. Nice.
Oh, groovy. That's awesome.
Yeah.
Streaming tools for the win.
Yeah, finally.
So I've got this guy here, and we're not going to be necessarily hyper close. We can get a little closer. Maybe I can do one of these and zoom in so we can see a little bit of the interaction. So first things first, I'm going to back up. I'm just going to turn this guy on. So we've got a power button.
And so that's just 4 regular old AA's?
Yep, we have our own custom branded cells.
I love it.
Of course, because we wanted to make sure you guys have access to ones that are good, nice and juicy for
it's getting tough these days. The battery quality, I feel like that you'll get at your average, if you're just buying the Amazon junk, right? Like you can get burned. You'll get some duds in there. Yeah,
no, I totally agree. And it's. We try to test everything. These are all rechargeable nickel metal hydrides, so you can see I got the neuron that's got the wall plug telling you to recharge them.
Fantastic.
But we wanted these to be plenty juicy. We're running a camera, microphone, sensors, lights, motors, streaming a Wi-Fi, all these things. And it sounds like a lot. And everybody says, okay, yeah, well, why don't you just have lithium and charge it over USB-C? I don't think that we need to lithium everything. I think that's actually a huge problem. Whole different topic of discussion. But believe it or not, on 4 AA batteries, you get about 7 or 8 hours of runtime continuously with this thing. And so
that's legit. That's a whole day of work right there.
It's a whole day of work. You're ready for a classroom. And in the context of us doing all of our grants and developing a high school curriculum, a lot of what we wanted to do was make sure that it's accessible. And so if you've got a classroom and, your batteries are dead, if this was on lithium, your class would be over before it started, right? But I can just pop these out. I can go down to in a pinch, get some alkalines if I really needed to. But you're off to the races really quickly. So real quick, all we do once we've got it, we're just going to connect to its Wi-Fi. And so I'm going to connect to its Wi-Fi, and we are going to set the robot aside here a little bit while we kind of check things out. And so I've got the color green on this Breitenberg vehicle because everything in my lab is blue. And so it won't really make for a great demo of tracking down an object if we were to do that otherwise. And so just to look at here, we've got green in the left field of vision, and that is controlling banking to the left. So if a green object is over here to the left, we're going to move that robot towards that. We're going to turn it, sort of bank into it. On the opposite side, we've got green on the right controlling this neuron. And when that fires, we're going to bank to the right. Simple. We indicate this by showing the right lights on the robot or left light on the robot. And when we want to actually run this, I will back this up. Put this guy here. Cue up a green object, but it's simple as pressing play. And so just to get back up here a little bit, I did want to show off the cool OpenCV stuff we're doing. So I'm going to zoom into our camera feed here. And so you can see this is kind of our visualization. You can kind of see how that dithering and etching kind of comes into play. Does that weird sinusoidal pattern, but tries to make it, you know, this etched landscape, which is kind of neat. And if I see a green object, and I can even probe these neurons electrically with these pins. So I see the orange and the blue trace for the orange and blue pin that I've placed. When I see my green object, you can see them activating. If it's only in my left field of view, or if it's only in my right field of view. So I'll put that on the table. We'll see what that looks like as an actual behavior here. I can basically just have this thing chase this around.
Love it. The quick little guy.
It's pretty responsive. 20 hertz doesn't sound like it's super fast, but you know, we're not competitive online, right? We just need to have some fly away here. Could be my robot that's giving us Wi-Fi interference too. I'm not really sure.
Yeah, maybe. Who knows?
Who knows?
You're back.
I've also been having problems with 5G versus 2.4, and it's a mess.
Computers were a mistake.
Yeah. I prefer neurons after working with them for quite a long time now.
Yeah. So, bringing it full circle.
So what else can you kind of do with this, just to show you a little bit about how quickly it is to change things? So you saw it uncontrollably was going towards objects. So I can add an inhibitory neuron in here, and I'm going to drag it, connecting to these two neurons. You can move this thing all around to reorganize things. And I can even group select all of the connections downstream by, hopefully, with any luck. Let's zoom in. There we go. You can multi-select by selecting the trunk here, and then I can set that synaptic weight really strong. Then I will look at the signal here. So we're looking at very close. So when this robot gets very close to an object, we're going to send a signal to this inhibitory neuron and stop activating these neurons when we see green. So the net effect is that when it gets too close, instead of it just kind of, you know, violently attacking things, we can press play, still track things down, but when it gets close, it stops. Even though it still sees green, we'll just kind of stop when we get too close.
Very nice.
And you can get more complicated, of course. So I could load up a whole bunch of different brains. There is more fun things that you can do. Really simple things. If you wanted to play with the microphone, I've got 4 neurons that are responding to my volume levels. And so you get a little visualizer here.
Very cool.
I can pause it. We can get into making brains that are listening for whistles. So if I whistle a certain pitch, I think I might have to adjust something. So this is where it's fun. So, you know, this was probably designed before I had this iteration of the robot. So let's kind of diagnose what's happening. This inhibitory neuron is going to turn these guys off whenever the volume is quite low. But maybe we actually want to gate that to be higher. And we don't want to ignore these lower signals. So I can change that range, which this inhibitory neuron is deactivating these things. So if I whistle now, or talk, it's detecting the pitches in my voice. You know, and it's making little beeps in response. So you can really just real time, you know, start to tweak things and, okay, which pitch am I actually listening for? Or which frequency range? That's the exciting thing about being able to do this, you know, really rapidly, is that you can make adjustments super quickly. So this is a cool brain. Uses remote control neurons. So hopefully I already have this prepared. And if I do, it'll pop up here. And if I click on one of these neurons, you'll see I've got this listen for input button. So when it's set to remote control, I can press listen for input and I can press a button. So that was the Y button. I can just go through here real quick and remap these instead of being a keyboard, map them to these face buttons on this controller. Great. And
Yeah,
so
those
I'll make
those
this.
little 8-bit do mini controllers have gotten really good in the last couple of years, I gotta say.
They really have.
They
And it's
used to
super
be
convenient for
kind of
these demos.
Yeah.
Yeah, I agree. And it's awesome just to be able to like have one of these little slick things to control the robot, and it's, you know, small as
And
the
it
batteries,
matches your color
basically, right?
scheme, so yeah.
Oh yeah, exactly. You gotta love it. So I've just remapped in like what 15 seconds while we're talking all these neurons, and they're going to different motors, so you can control more than one motor direction at once. If I control forward and backwards, these will cancel out. But if I control two forwards or a forward and reverse on different motors, things will sort of add together, right? And so I can just press play now, and I can look at these signals if I want to, just so we have something to kind of visualize here and see what the camera feed is. But now I've got a remote control car. So within a few seconds, we've made this thing, you know, a little remote control device. It can beep its horn. Sort of a weird, slow robot horn. So maybe we want to make that more like a clown horn. So we're going to actually boost that octave, go to like a really high note, and then we're going to go try it again. So now we got a little trombone. And then maybe we think maybe it's a little too slow. So we can just jump in here, boost these up, full throttle, full speed ahead, right? So turning is still slow, but we can get out of there real
Naruto
quick.
run there, yeah.
And you can do more than one motion at once. So you can turn in place, you can back up, or you can do a banked turn by doing both at once, right? If I do forward and backwards, it's going to go forward slower because we accelerated forward so much. But
I can just really see the value here for classrooms, especially like what a great way to walk people through like these concepts. And also I love the art style here, very Dr. Seuss.
Yeah, 100%. Yeah, thank you. It was fun illustrating all these and getting it to all align right. And the neurons themselves are like a generative algorithm, so each one's unique. And then we draw these, you know, curves and everything, obviously, between the connections. It could be straight lines. It could be maybe a little less hairy, but where would the fun be in that? So there's so many cool things that you can do. On the more like educational side, we can get into actually starting to explain some real neuroscience concepts. So if I go in my little lab notebook here,
Oh, I think we lost you again for a sec there. Hopefully,
anywhere in field of view.
You're back.
Yeah, sorry about that. We'll back up here a little bit. So I just wanted to get into showing off a circuit to start. When you start getting into the more neuroscience terms and things that we learn in education, what that kind of looks like. So I've got a simple brain here, red light, green light. And we've got a bunch of fun sound effects throughout. You'll kind of hear, you've got spiking happening when you're dragging a neuron. Drops in, makes some sounds. You clone and delete things. If you're stretching an axon, you get a lot of fun sound effects here and there.
Very important.
Oh yeah, I mean it's very inspired. You know, speaking of the Mac back there, very inspired by like CD-ROM serial box games and stuff. We wanted to make it kind of that level of fun.
Those.
But oops, now with PhD level neuroscience concepts. And so in here, we've got a circuit that's playing red light, green light, very, very simple. And I'm actually going to add a red connection to give us some visualization to that. But the idea is that let's look at the lab notebook. Let's learn about what this does. So we've got our notes. You can rearrange your notes if you wanted to. You can make your own notes where, okay, maybe I wanted to say, hey, I added this red connection and I want to describe that. Oops, this one there. I can describe what I just did, and that becomes part of my annotations. And so you can make your own like presentations when you're sharing and doing science communication, which is really cool. But here's how it works. We've got our first neuron. It's responding to green anywhere in its field of view. And when it gets a signal, it's going to stimulate this first neuron. And notice that these have really thick lines back and forth. This one goes to this one goes back, this one goes to this one. It creates this sort of infinite loop, and it looks like a little infinity sign. This is called a recurrent pair of neurons. And the idea here is that this is all over in your brain. Neurons will form these clusters to form sort of working memory. And basically the idea is when you start stimulating one of these, they'll start kind of turning into an on switch. And they'll just fire back and forth, back and forth, back and forth like crazy. But then if we, and we'll have an associated behavior, we'll spin around or something. But then if we take this and we inhibit these guys, it'll finally turn them off. And so different inputs will turn on in a memory, different ones will turn off in memory. And this recurrent pair of neurons, we call it, is one of these really important building blocks in the brain. So what does that look like? I can tell you this demo is not going to work right away. I'm going to show this a green object in front, and I'll tell you why. It does kind of work. Let me grab a, looks like we see a lot of red in the room right now, so maybe we can change the red activation color if we need to. But surprisingly, it does activate. Sometimes this demo doesn't work because we've made that connection very weak. So whenever we see the green in significant enough view, you can see I am seeing in our vision, we are seeing green, but we are also seeing red at the same time. My brown table here is detected as red often, so we can adjust that later. But we could also maybe make it a different target. So maybe my hand as a person can make this stop. And I'm going to make green more sensitive here by just boosting up this synaptic weight. So it might be hard to put my hand in front. It might over-detect. You see it's going forward. And then it sees my hand there. You can see we got the outline of YOLO kind of appearing. These are why these demos are fun, because it's never going to do things you expect, right?
Yeah.
Little Wi-Fi latency, but it can detect me when it looks at me a lot easier. So now I've got the red. But if I look at the green, might be spotty again there.
We got your back.
Okay, cool. Yeah, I noticed that this guy was stuttering a little bit on the connection too. So maybe it is some interference, channels, bands, networking, the good stuff. We also have a lot of fun personalities for this thing. So I don't have too many costumes. I will give it what I have for this. So that we have these newer connectors. I actually had a bunch of costumes before. So like on a previous iteration of the robot, you can see the hardware is physically looks a little different. I had some cat whiskers, and we have some ears and all sorts of costumes. I'm in the middle of updating all of those for the new style. We have this really cool, these slots, which are conveniently large enough. You can kind of peek in there, conveniently large enough to feed a servo wire through for the future. But
smart.
We can snap them in and take them on and off and snap them on, and they're nice and strong, so I can actually grab him by the wing here. We also are getting into doing some other weird posable attachments. So I have these nice little spheroid shapes that have our connector and then have a sort of 8-way socket. And they're at a fun angle that you can then just use the same piece over and over and over to create various, tentacles and arms. And so later when you want to do like you want to have your robot draw something, you can give it this extendo arm and you can mount a pen on it or, something else. Maybe another sensor, who knows? And
You
so
are
there's all sorts of different things.
an absolute menace with the 3D printer, Alex.
Oh yeah, it's been that's really where a lot of my career started. But I really wanted to make this thing as fun as possible. It's probably overwhelming, but hey, like I was always inspired by what you could do in the Arduino days, and they didn't really hold anything back, right? So we want to make sure that people have every possible avenue for finding some creative expression and having some fun with this thing. So all these costumes will be open sourced, and I think I'll even have it's actually our first stretch goal to get a lot of these released and finished off. But then I'd like to build I have a beta of a accessory development kit. So it's got the subtractive forms of the enclosure and the connector itself. So you can make your own little accessories. And, there used to be that trend in Thingiverse where they'd put beefy arms on everything.
Yeah.
I don't know if you remember those days. So hopefully somebody will
arms, right?
Yeah. Yes. Hopefully somebody will give our guys some beefy arms. I mean, I'm excited to see what people will kind of make. We should be able to sculpt whatever you want from, different hats. A lot of animals, I think, are really good. You got a little propeller hat here.
The propeller beanie, of course.
This is for when he can count. We also had like little glasses and monocles and a bunch of stuff that's in our office, not at my home lab right now. But if we were to treat it like a creature, we also can do things like make it act like a cat. So this cat's going to hunt down a red object, like if it was a ball of yarn. And it's going to meow at random. So this is one of those cases, we've got these two neurons that are just triggering this meow. This whole brain is only, mind you, 4 neurons, 4 brain cells. And we got a pretty dynamic, little robot that's playing around. It's batting at the red object. If you had a ball, it would chase it around. And that random meowing is because cats don't really meow for any reason. They may meow in response to stimuli, but more often than not, they're just kind of making noise, right? So we'll pause that for a moment. On the more complicated side, you can also make music instruments. This adds 1 more neuron, so we've got a really slow theremin here with the Wi-Fi right now.
It reminds me a bit of that. There was a game Nintendo put out for called Electroplankton.
Oh yeah, I think I remember that one.
Yeah, it was for the DS, I believe. Very cool, creative little artistic thing.
Yeah, it's super fun. We'll enhance a lot of the sound samples and things as well before launch. Make things a little tighter and more responsive. I think I have some latency in my recordings. But yeah, there's so many cool, like, fun things that you can do with it. And then you can get into the meat and potatoes of like what's real neuroscience that we're aiming to talk about looks like, right? And so I'm going to pan up here again. And so this circuit has 5 neurons, right? And this starts to talk about neurological disorders. And so a lot of what we find in the brain with a lot of neurological disorders is that a lot of them are inhibitory dysfunction. Interestingly, there is a certain proportion of excitatory and inhibitory neurons in the brain, and usually they're at quite a balance. There's this really famous paper that came out a long time ago that was debunking free will because they were able to do like some prediction of excitatory responses in the brain before people were able to do actions, before they made a conscious decision about inputs. But really, the brain is this big simulation tool. We're constantly simulating the world around us. And so there was this follow-up paper somebody else wrote where they basically were, and I'm going to butcher this, but it's been a while since I've read it. They basically were not able to get the same effects in a certain region of the brain with inhibitory neurons. And what this kind of, is a showcase to, so it was called the free won't paper, if you want to look it up. At least that's the shorthand, vernacular of it. But the idea here is that our brains are constantly running simulations of the world around us. And so to have agency, we need to allow these simulations to, take course so that we can plan our actions ahead of time. But then if I have to make an impromptu decision, it's a lot easier to hit the brake than it is to, make a larger coordinated move and do a whole plan of actions. Part of your brain is going to be doing this planning continuously, readying your next action, and then another part of your brain is looking at your attention, and then it's going to be able to inhibit things when you don't want them to happen or decisions that we don't want to make. So looping that back in, this is a brain that does a complex series of actions. So we're familiar with, in regular coding, loops. I'm going to do this thing, I'm going to serialize, progress through these motions. And this isn't too dissimilar. It's going to look very dissimilar. And I could describe this more in detail, but essentially we have an input coming from the distance sensor, stimulates a pair of neurons, which we simplify things by using these delay neurons. And if you zoom in, you can kind of see that they're little clocks, and the clock hands correspond to how much of a delay they have. So you can kind of get a little bit of an at a glance version of the story here. So I should boost that and make those match. And so you still with me?
We sure are.
Perfect. So we basically will stimulate this pair, and they'll start firing indefinitely. We'll then cascade that down to this first delay neuron and then to the next. As soon as this first delay neuron starts to fire, we send in the signal to an inhibitory neuron, which stops any further input from happening. So when this first pair starts firing, it stimulates not just this neuron, but also a motor action on either motor and a certain light. Then when this one fires, we stimulate the inhibitory neuron, we pass the signal along, but we also have a different motor command that we are issuing. Then it goes to the last neuron, which continues to inhibit that first pair from further input, has its own associated actions, and now we have a 1, 2, 3 step action sequence, or a fixed action pattern, we would call it in neuroscience, or potentially a central pattern generator is what this is. So in practice, we've got a robot, we're going to press play, and I can probe and look at all these signals if I wanted to. So maybe I'll look at this first pair and the next inhibitory neuron, and let's zoom into this so we can see our signals here. If my finger can get to it. Wrong trigger here. All right. So the orange is our first signal. And so when I go to stimulate this guy, I'm going to take off its wings so that we... All right. We're doing a lot here. So when I first stimulate the distance sensor, you'll see that first one goes live. You see those two signals had two different periods there. We got a backwards, a rotating, and a moving forward and to the right. And so this is the pattern it wants to do. It wants to always, and I'll just get this out of the way here just so we can give it some more space here. It's sort of doing a sidestep. And so stimulate it, and it's going to sidestep an obstacle that comes in front of it. So this
sort
is
of like your robot vacuum cleaner or whatnot.
Yeah, and this is also kind of like a reflex. I mean, we make coordinated movements all the time. Talking, I don't think about all the micro motor movements that I have to make for every individual muscles, right? I think I'm going to get out of my chair. And so we have these circuits go from the brain through the spinal cord, all these things that produce these patterns of locomotion. And so I can say I want to get up out of this chair. I have that thought. I'm flexing all these muscles in a particular order to, boost myself off the seat, stand up, all that sort of thing. And so this is kind of replicating what that looks like, right? And you can see as soon as it got the second stimulation, if I continue to stimulate this, it always goes red, yellow, green, even if I continue to stimulate it. And that's because we have that inhibitory neuron. It's doing its job. And if I were to look at that signal, you can kind of see, if you were to zoom in here a little bit more, this signal gets dipped low, this orange signal, and then it slowly comes back up when we're done. That's that inhibitory neuron lowering that membrane potential. So you see it kind of rises back up there. And so in the brain, many neurological disorders, you might have lack of this inhibitory connection. So we just deleted that real quick. And so now, all of a sudden, it's not stopping. And you can see all these traces, they're going like crazy all the time, right? So that's one possible, that's like having a seizure where we can't stop an action. But you could also
Fascinating.
get rid of a connection from one of these loops, for example. So now I give it a quick pulse. It kind of looks like it's doing the right thing, right? It's kind of doing the right thing. But what happens if we continue to stimulate it? Now look at these signals. Now they're overlapping here, right?
Robots only do this when they're in distress.
Yeah, exactly, right? The simple idea here is just that, these are the sorts of things that are presenting themselves in the brain. There's all sorts of neurological disorders. They present themselves in different ways. If we can explain these without like singling people out, having a better understanding of them from an earlier age, be able to abstract some of these things into, an anthropomorphized robot instead of, like I said, singling out students or making it a topic that is non-discussable in, earlier education. But it's also something that I think is important to know. You look at things more complex neurological disorders like schizophrenia, for example. We were mentioning that our brains are constantly running simulations. And so we have a section of our brain that inhibits these simulations. And so when we want to do something, we just allow that simulation to kind of run its course, right? We give it access to the rest of the brain that controls locomotion, et cetera. And we're not thinking about every possible option in our conscious selves. But somebody with schizophrenia might not have those types of inhibitory connections or impulses. And so their brain is seeing quite literally all those simulations that are running. So hallucinations and things like this are a byproduct of a lack of inhibition in this case.
Yeah, it's a really great bit of insight there. Thinking about it more now of a way to sort of increase empathy, I think is a really interesting sort of knock-on effect of this really fun, project.
Yeah, I think if we really want to actually tackle these hard problems, we need to abstract them enough to be, on the table for discussion, right?
Yeah.
And
Yeah.
I think if they're too heavy and if they're too concentrated, it's difficult, and I think a lot of people don't really think about neuroscience until, really probably at all. A lot of people, honestly,
Until they have to, right?
but until you have to, you don't think about neurological disorders until something happens. You see therapists, or you're interacting with somebody in your community, whatever it is that you have to adapt and you learn. And I think most people in the modern era with access to the internet, I think there is a lot more positive culture surrounding this, but I still think that we can do more. And I think being able to understand things, not completely mechanistically, this is, an oversimplification of what's going on in the brain, right? We're not talking about neurotransmitters. There's a lot more going on. At the same time, the messaging is really what's the end. We're looking at sort of the end product of what these neurons are really trying to get at. And I think it's useful to think about things in a way that we can actually make these associations that are, just more, like you said, empathetic. I think it's super important.
I think so too, and I think y'all have done a great job here on SpikerBot, and I know you've got some other stuff out there. There was like we got a couple of questions about the plant spiker box, actually. which I'm personally interested in because I've built quite a few of sort of monitoring things over the years. I have a whole bunch of houseplants here, and I've always been more interested in like what are they feeling, right? Like
Totally.
what's going on with them in like a way that I can go ahead and bring myself back on here.
Yeah, I'll pop us back on here, talk a little
Yeah,
bit.
fantastic demos. We've gone way over time, but I don't care.
Yeah, sorry about that. Yeah.
No,
And
it's all
sometimes
good.
it's fun, man, and I have the problem with that as well. So, yeah, to answer your question about the plant spiker box, so I mentioned that earlier in the talk. So we started doing a lot of electrophysiology recording equipment and building these different analog amplifiers. So much like this brain is sort of like an analog computer, um, our original circuits and a lot of things that you can currently buy on our website, backyardbrains.com, is a lot of this electrophysiology gear for you to get hands-on with stuff. So in an insect or a human, there's different ways that we conduct electricity that we can measure through these neurons. Just like in our simulation, we have a membrane potential, there's a voltage associated, but we are electrochemical with electro on the front end of that equation, right? Because that's sort of the dominant thing that we're able to measure. It's the higher speed information exchange. For a plant, we usually say that they are, I mean, I would say it's more like chemical electric. And so like where we are transporting through electrical impulses information, we do get an actual electrical impulse, but plants work at such a different scale that a lot of that is, mechanical transport, capillary action, these sorts of things. So where I have tens of meters a second to send a message, a plant will actually send signals mostly for really important stuff like wound response in the order of millimeters a second. So the plant spiker box is
Lost you again for a sec, but you are back.
the plant spiker box is spiker box. I know it's confusing. SpikerBot, SpikerBit was our last year's Kickstarter. Spiker boxes. It's part of the fun.
Yeah,
Get them all.
yeah. I'll bring up the plant. We actually have a question from the audience here, and so I'll bring up the plant spiker box
Cool,
on screen,
yeah.
so we can talk about that for a moment because we had a question from here's the plant spiker box. You can find this on backyardbrains.com website. One of our viewers over on Zoom, Martha, asks, what would it take to add a camera to the plant spiker bot? Any plans supporting ESP32 boards, especially ones with a camera hat?
Yeah, so interesting. So the plant spiker box, I know it's confusing. I just mentioned this, right?
Yeah.
That is a device that works wired right now to your smart device. And then we have a separate app that's the Spike Recorder. And that's for all of our electrophysiology stuff. Now, there are some signals that are broken out. There's a little bit of a breakout. It's a lot more DIY. But what this is doing is it's amplifying these really slow moving signals. So I'm not sure if I got cut off earlier during this explanation, but plants are moving their electrical signals are mostly chemical in nature, and so they move at millimeters a second. But when you elicit a wound response, like cutting a leaf, burning a leaf, high wind, you'll actually get an electrical signal. And because it moves so slowly, it's not an artifact because I'll take scissors, I'll cut the leaf, I'll have two electrodes downstream, one in the ground as a reference, and then one somewhere on our stem of the plant. I'll cut a leaf. Seconds later, you'll look at the recording, you'll see a dip and a spike, and then a relax. You'll see this, essentially it looks almost like a textbook neuron action potential. It's the same biphasic potential, we call it, that is just like this, energy optimized function for translating information. So that being said, that does have, I believe, an output port. We might be able to manipulate it. I can get you a more firm answer on that if maybe we can share an email later. I'm just Alex at Backyard Brains if you want to email me directly. But if you want to connect something to the SpikerBot, your best bet would be to simply route it over to some sort of Bluetooth HID device. So if you could pull that signal out, which you should be able to with hardware and like another ESP32 and monitor some of the pins.
I'm wondering about, yeah, I have a little Flipper Zero. I'm like, I wonder if I could just hook the Flipper Zero up to it as a remote kind of monitor, right?
I'm sure you could, right? Like the Bluetooth and the HID device and even like hardwire, that goes to your app. So the robot itself doesn't need to have its firmware updated and look at all these protocols, right? Like if you can get a HID command to that device that runs the SpikerBot app, then you can then go in, click one of those remote control neurons and set it to whatever key press or joystick event, and then you could have it trigger. So you absolutely could get like a, SpikerBot that's just chilling, and then, it's a really windy day, or your house is, use it as a smoke alarm if your house burns down or something. You can have something where you trigger this based on a wound response of a plant. It's not like you see a lot of these, what I would more consider toys that are amplifying plants, a lot in the music space. They're usually measuring just like the simple resistance and, mechanical artifacts of jostling leaves around, that sort of thing. You'll pick up some of that stuff, the moisture in the air. But the signals that we're trying to amplify with the plant spiker box are the actual action potentials, the messaging signals that they send. And they're just super, super slow. So
I saw some interesting, you chose the plants very well, I think, because I saw there was a Mimosa pudica, the sensitive plant, as it's called sometimes, the shame plant, as well as some Venus flytraps, because they have, physical responses to stimuli in ways that most other plants do not. And so I thought that was pretty clever.
Yeah, and that's kind of an interesting thing too. I mean, when we started with the insect electrophysiology, we actually, our first Kickstarter, which was done 12 years ago or so, I think, was for the Robo Roach. And this was what we consider mankind's first commercially available cyborg kit. And it's a little, we still sell this actually. It's a $100 backpack that you can, I lost your audio now though.
We're back. Don't worry about it.
Okay, cool. Sorry. But that's mankind's first commercially available cyborg kit. You would do a small surgery on a cockroach, use this as a neural stimulator to learn about neural stimulation directly of nerves. But there's all these experiments that you can do with insects and with humans, non-evasively with humans, of course. But you can do these experiments where you actually stimulate. And so with the plant stuff, you can actually take a Venus flytrap, which has these little hairs, right? Mm-hmm. These hairs are the detectors. And so it's one of those rare plants that has a messaging signal that's not a wound response. And so in a Venus flytrap, there's only a few of these signaling hairs, and you have to stimulate them fast enough rate to get that trap to actually close.
And multiple ones as well. It's like a couple, you have to do it a couple of times. Yeah.
And if you're careful, you can just stimulate one hair, not trigger the trap, and see the actual messaging signal. And so what we'll do is we'll actually amplify that. We'll then take that signal and we'll pipe it over to the sensitive mimosa, which can be stimulated similarly like to neurons in insects, or like the TENS unit muscle activations for people. And so you can stimulate a hair on the Venus flytrap and make the sensitive mimosa go to sleep, which is a pretty cool demo.
Wow,
so
that's fascinating. So you guys make some incredibly cool stuff, I got to say.
Thank you.
We want to link it all here
next. So yeah, please.
Got a couple more questions here, and well, actually, let me pause here. People have been very patient. We're going to do our trivia giveaway here.
Oh yeah, awesome.
Let me post. So I will share my screen. So thanks for your patience, folks. I know you are waiting to win this free OpenCV University course, and we're going to make that happen here for you. So the way this works is I'm going to ask a trivia question based on today's presentation from our awesome guest, Alex. And the first person to answer that question correctly, wherever you're watching, on YouTube, on LinkedIn, on Twitch, on Zoom, wherever, first person to answer that correctly will get the OpenCV University course of their choosing. You can see what courses are on offer by going to opencv.org/university. And today's question is, we have talked a bit about SNNs today. Chat, what does the acronym SNN stand for? Answer in the chat to win. First person to answer wins the prize. So let us know what you think here. Seems like, Alex, your Kickstarter is doing pretty well. I think last I checked, it was about to cross 30K. I'm hoping we can continue to help boost that for you, and it's a big success. It looks like we've got, so in this case, some people are answering. We got a correct one here. Looks like Anaruda on Zoom answered spiking neural network. That is the answer we were looking for. There's also, of course, somebody said synthetic neural network, which, yeah, that is also an acronym people use, but that's not what we were talking about today. So congrats, Anaruda. Please send one email to me, that's Phil, at opencv.org, and we will make sure that you get the free course that you pick. Go to opencv.org/university, pick any one of those courses, let me know about it, and it'll be yours. Congrats. So, Alex, we got a few more questions here from the Peanut Gallery in the global OpenCV audience. Let's take a look-see here. This one's more of an interesting sort of comment from YouTube. There was an experiment, Carl Lashley's rat maze experiment, like 100 years ago. He kept removing brain tissue to find the memory spot, but the rats still remembered the maze. Super interesting. Reminds me of like the planarian worms experiments.
Oh,
I don't
yeah.
know if anybody out there's a fan of the Swamp Thing. Alan Moore's run on the Swamp Thing comic in the 80s. I'm a big fan, and he talked a bit about that in that comic series. That basically I'm gonna probably butcher it here, but like the gist was basically that there was like generational memory in the bodies of these worms that you could basically kill the thing and it would still remember things that had happened in its previous life, more or less, right? Is that not the case?
Yeah, I think it's there's so many things that I think are really hard to pinpoint, just because there's so many systems at work. Like we were looking at earlier, a dozen neuron circuits, maybe 24 or so. Even insect brains have hundreds of thousands of neurons minimum, right? And what a lot of these, or ganglia in the case of an insect, but a lot of these circuits are a lot more efficient than even what I've shown you guys today. And so in our brains, we have these cortical columns. And so this big part of your cortex is doing a lot of these calculations, and it's wired structurally very similar. But a lot of this is, building these associations between different events, kind of redundancy. And so that's kind of like one of the interesting things is that I don't know if we really think about redundancy in code in the same way, right? This is another way where we really are sort of different. You might make more redundant checks, and okay, I know that this happens, I have to check here and whatever, but unless your silicon physically breaks down and alters its structure, like you're pretty okay to not have two pieces of code that are doing the exact same thing, right? But in the brain,
Right.
all these things are happening in parallel because it's like the noisiest, the squeakiest wheel gets the grease kind of a phenomenon, right? So if a lot of things in your brain are telling you to do something, your intuition maybe, right? Like you're more likely to do this thing. And so there's power in numbers in the brain, whereas that might not be the case with computers. So yeah, it's super interesting. And there's this whole
Agreed.
field of epigenetics even that kind of goes beyond things, where there's proteins and things that attach on top of DNA that can be, hereditary and affect development. So there's so many layers to it. And memory, that's complicated. Let's just say.
That
This
is
why
one
we
way to
didn't
put it.
That's why we need people, interested in these fields to really learn what's going on, not just blindly picking apart at brains.
Yeah, even
Or
rat or roach brains. You
yeah,
should probably have.
Yeah, you can go ahead and do it with a robot safely without having to get too squeamish about it.
Yeah. You talked about a book earlier. Folks were interested in that. Can you put the book back up on screen for us?
Yes.
Yeah, vehicles,
This
experiments
is like
in synthetic psychology. Okay.
This is like 1984, I believe, is when this was originally published. It's by Valentino Breitenberg, Braitenberg. Breitenberg.
Well done. You got it.
And so this is a really good, really good piece of literature, and it's got some fun illustrations, and it gets into some like. This is also like kind of our style too, which is just so funny. Like just.
Oh, lost you again. You're back.
It gets into some neuroscience stuff, but it also gets into some weird concepts trying to find a page of like, they just got these sci-fi illustrations and sort of some wacky stuff in here too. That's just like nonsense creatures and things to imagine, but it goes over a lot of the concepts we're talking about and, different patterns of networks and
wow. Some of those illustrations really were very Ralph Steadman like inspired, sort of
totally.
Gonzo.
I mean, this is all kind of that era, right? So
yeah.
Cool. super good. And it's a short short one, not too many pages. What do we got?
Yeah, we'll have to check that one out.
Not even 150 pages. So
I'll have to bust out my handy dandy library card and go over to the San Francisco Public Library and see what they got.
You should probably be able to find it. It's in this space of like computation, neuro-robotics especially, right? It's a instant classic, like I said. So
okay.
Yeah, the first circuit you learn in our brain is basically directly from this.
Love it. We've got I think time for one more question here. This is sort of a broad one, but I liked the way Danny phrased it. So Danny DDT on YouTube. I'm trying to understand where SNNs really shine beyond use cases already covered by existing methods. What is a clear practical advantage in industry? Like, have you thought much about this? Like, is there? I know you're sort of on the education side here, but I'm sure that you're an inquisitive guy, and this has crossed your mind.
Oh, totally. And there's so much that I nerded out with you guys about earlier, but there's also so much that I have planned for this that's not even there, right? Like we mentioned neurotransmitters, but more importantly in the brain, there's things like plasticity. And so a lot of what we're doing right now in the era of AI is done with a lot of reinforcement learning. And so you might give it a bunch of training sets and then give it like, weights to say, this was good, this event was bad. But this is also not how we do it, right? I mean, we do, I think, some reinforcement learning. You have dreams, you can condense memories and things like that of things that happen throughout the day. But there's also this huge category of like, real-time learning. I meet a new person, he says his name is Bob. I've got to use that information right away and try to remember this guy's name is Bob when I talk to him. And, we learn things at a much faster pace. I don't have to go to bed, coalesce the information from the day to know what this guy's name was, right? I mean, sometimes it is that hard if you're meeting a lot of people. But when you get into things like plasticity, this is the ability for neurons to create and destroy their own connections or, increase and desensitize the weights. Start doing more real-time, now I'm a blank out on the term, but not just reinforcement learning, but sort of real-time learning. I'm going to have to come up with the term again. Totally blanking on it now. But there's a different style of learning that you can do with the spiking neural networks. I also think that they're useful in industry from the perspective of having more lifelike behaviors and being more, computers run extremely fast, right? So I don't think there's any issues with classical computers driving actuators, but there is something to be said about the instantaneous responsiveness. And I think in the future, if we're doing this for education purposes, get people in robotics, get people into neuroscience, and we have a robot as a wireless peripheral, maybe a future version of our robot will actually put the spiking neural network on the device. And once you start doing this, this is where I think spiking neural networks do some really cool things, because technology does this not because it's, a fun way to do things and it's quirky, but it's super efficient. And all biology is always trying to like be as lazy and energy efficient as possible, do the minimal amount of work to survive. And so the way that we exchange information in a spiking neural network is very efficient. I mentioned earlier, it has a lot of redundancy. And so it's able to adapt. And if you have plasticity, which eventually we can get into, you can learn new things sort of real time. So these are just some of the small things that are kind of exciting. When you actually deploy this onto real hardware, the efficiency gains potentially could be huge, just in terms of being able to do complicated operations. We already see some of this stuff with like tiny machine learning models and things like this, but we're to go further with, spiking neural networks all the way down. I think that, you leverage these things together, you'd have a really lightweight, efficient thing, right? I don't think lithium ion is the solid battery technology. It's really good for things that we have no other source for. But, as technology gets more efficient, our reliance on crazy chemicals and other things is also going to go down. So if we can get, useful robots using spiking neural networks and maybe decrease the power load, that also could be a huge application. So lots of things actually. But very different from what we're used to, I think.
Yeah, great points there. Thanks for the thoughtful answer. I think we just set a record for the longest episode of this show ever. But it was worth it.
Sorry about that, but it was fun.
No apology necessary. This was fantastic, man. We had a lot of folks sticking around through the whole episode too, which is really great to see. Thanks so much, everybody. Any final thoughts for the audience, Alex?
I just want to thank everybody for staying with it through the end and giving some good questions. And the only other thing is, if you are interested in all this stuff, definitely check out our Kickstarter. Once again, that's SpikerBot. And he's got the little QR code up here. You can also check out our stuff at backyardbrains.com. Tons of tutorials and examples. We have other stuff to experiment with plants, humans. I didn't even get into controlling this with your muscles and your mind, but you can do that with SpikerBot as well. It's our first really cross-linked product, so you can actually use your muscle signals as your remote control. Exactly. So there's really not enough time to go over everything it can do. It's a whole new way to look at things, and we appreciate your time. And thank you, Phil, for having me.
Yeah, thank you for being on the show and the awesome demos and everything. Yeah, please scan that QR code on the screen and check out the Kickstarter campaign for SpikerBot. I'll be watching it closely myself, and we'll link some of this stuff on the OpenCV newsletter and socials as well to try to drive some more traffic. It's a fantastic product, super interesting. My brother George is a school math teacher, and I'm thinking
awesome.
like, oh man, he needs one of these. Like when George's birthday isn't for a while, but I might have to maybe for Christmas.
I can use it to explain why math is actually hard, right?
Yeah, definitely. All right, folks, we're going to call it a day here. Thank you so much for watching and joining us every week. I think next week we are planning to talk a little bit more about OpenCV 5, which is imminent. I swear, it's actually happening. Ooh. It is coming very soon, and we'll talk a little bit more about that with some of the OpenCV team next week. Same bat time, same bat channel. Take care of yourselves out there, folks, and take care of somebody else if you can. Have a great day wherever you may be. Adios.